So let's review the properties of electric charges once again. The electron, which has a mass about as small mass as shown here, has the charge which is minus E, and the number is shown here. And proton is in fact much heavier. As you can see, 10 to the power of minus 27 is larger than 10 to the power of minus 31 by about 1,000 times. So proton is much heavier, but the size of charge is in fact the same. Only the difference is their sign is minus and proton is plus. And then the neutron mass is very similar, not exactly the same, but very similar to the mass of the proton, but it has the charge 0. So as you can see, these three most important subatomic particles have different masses and different charges. Some are similar, some are very different. Basically, all of them are explained in terms of elementary charges. And in fact, atoms are electrically neutral, even though it contains many electrons and protons, because the number of electrons is equal to the number of protons. And in fact, the number of electrons for any atom is equal to the atomic number. And the materials can become charged when a small portion of electrons are separated from atoms, and this is called ionization. For example, an aluminum atom, which is given by the symbol Al, can become ionized and become positively charged when 3 electrons are taken out. So this is not an aluminum atom anymore. This is called the aluminum ion. So making an ion from an atom is called ionization. And then the unit of charge C, which we already have seen, is read coulomb. And then this word coulomb comes from the name of a French physicist who discovered the Coulomb's law, which we'll soon see in some of the next slides. And how large is 1 coulomb? 1 coulomb is defined as the amount of charge that flows when 1 ampere of current passes for 1 second. Well, we have not yet learned what 1 ampere is, but well, you have to define either 1 coulomb first or 1 ampere first, and we will soon see later how we define 1 ampere. But here, right now, let's try to remember that 1 coulomb is defined as the amount of charge that flows when 1 ampere of current is passing for 1 second. And well, so basically the charge is related to the current. So the current is in fact the time derivative of a charge, or in other words, the charge is the time multiplied by the current. So that's how the coulomb and ampere and second comes in. So basically 1 coulomb is 1 ampere multiplied by 1 second. Okay. Now, let us describe the force between charges more quantitatively. As you know very well, in physics, we always try to express physical properties using mathematical formula, and that's what we are going to do here. Suppose there are 2 charges, and we call the first charge Q1, and then the second charge Q2, and then suppose these are separated by the distance r. And then we will always find that the force between them acts along the line connecting these 2 charges. So let's take a look at the figure on the right side. There are 3 figures. The first one of them shows the force between 2 positive charges. As you can see, the arrows which represent the force are lying exactly along the line connecting these 2 charges. And these arrows are pointing away from each other, meaning that these two charges repel each other. And then in the second picture, there are two negative charges. Again, as you can see, the forces are actually pointing along the same direction as in the first figure. And whether there be two positive charges or two negative charges, the charges of the same sign will still repel each other. And in the third figure here, there is one positive charge and one negative charge. And again, the arrows are lying along the line connecting these two charges. But as you can see, they are pointing toward each other, meaning that these positive and negative charges are attracting each other. So we can summarize that the force will be attractive for charges of opposite signs, whereas it will be repulsive for the charges of the same sign. Now we have seen the direction of the figures. Then how strong is the figure? How strong is the force? The magnitude of the force or the strength of the force is expressed by the Coulomb's law. And then the name Coulomb's law suggests that this law have been figured out by a person named Coulomb. And what he found is that the size of the force between these two charges is proportional to the size of each charge, Q1 and Q2 in this case, and also it is inversely proportional to the distance, inversely proportional to the square of the distance between them. And then here in this equation, the K is simply the proportionality constant, making a connection between this size of the charges and square of the distance to the size of the force. And then this proportionality constant has a name like Coulomb's constant. And then numerically, it is equivalent to 8.99 times the 10 to the power of 9 Newton meter square per Coulomb square. And let's think about why this constant has a very strange unit like Newton meter square per Coulomb square. It is simply because in this Coulomb's law, the left-hand side is the force, while the right-hand side includes two charges and square of the distance. So one of the roles of this constant is making a balance of units between the two sides of the equation. And then there is another expression of the Coulomb's law. Now in this case, the Coulomb's constant K is replaced by 1 divided by 4 pi epsilon naught, which looks a little bit more complicated. So here, the epsilon naught has a name like electric permittivity of free space, and numerically it is equal to 8.99 multiplied by 10 to the power of minus 12 Coulomb square per Newton meter square. And then apparently it will be much simpler to use Coulomb's constant. Then why do we need this second equation? It is because eventually in the next chapter, when we are trying to learn Gauss' law, this expression will actually become easier. So that is the reason, and just let's wait for the next chapter to see a real example. And one important thing you have to remember about this Coulomb's force is that it is also one type of force, therefore it has to be a vector. If you remember what we have learned in the spring semester, especially what we have learned from Newton's law, is that the forces are actually vector quantities. So therefore, the Coulomb's law must also be written in vector form, strictly speaking. And in this figure on the right side, now the picture is drawn to represent three-dimensional view of the force acting between two charges. And then let's think about the first force, which is written as F2 arrow pointing 1, and then this is the force from the charge 2 acting on the charge 1. So therefore, it is actually this arrow acting on the charge 1. And then, as you can see, the sides actually looks the same as in the Coulomb's law, but there is a part representing the vector, actually the difference of the position vector between them. And then this difference in position vector, R2 vector minus R1 vector, is actually representing the line connecting these two charges. And one thing you have to be careful is that in this equation, here we have 3. Here. Okay, wait. I'm sorry. So here, wait. So here, okay, here we have 3 instead of 2. So why do we have 3 here? The reason is that in this expression of the vector, this actually includes the size of the vector. So therefore, because the size of the vector comes into the numerator, we need one more r in the denominator to compensate it. That is simply the reason, and nothing actually has changed in the Coulomb's law. And then in the second equation, expressing the force acting from 1 onto 2 is actually the same force with the same size of the Coulomb force, but only the difference is that now direction is opposite. So therefore, you can say that force from 1 acting on 2 is equal to the negative of the force acting from 2 onto 1. And then before we move on to the next slide, let me ask you a question. Now this Coulomb's law looks very similar to the Newton's universal law of gravitation, which we have learned in the spring semester. As you can see, the only difference is that instead of charges, now in this Newton's universal law of gravitation, we have masses, and Newton's law includes the constant g, and Coulomb's law includes the constant k. But overall, they look exactly the same. So why is it? Please think about it, and we will discuss the reason during the classroom lecture.